Selected Area Electron Diffraction SAED is a technique used in a transmission electron microscope, TEM, to study the crystal structure of materials at a very small scale, often down to individual grains or nanoparticles. In this method, a thin sample is illuminated by a parallel beam of high-energy electrons. When these electrons pass through the sample, they interact with the orderly arrangement of atoms in the crystal and are diffracted according to Bragg's law, producing a distinctive pattern of spots called a diffraction pattern. What makes SAED's selected area is the use of a small metal aperture that allows the user to choose exactly which tiny region of the sample, such as a single crystal grain, the diffraction pattern is collected from, while blocking electrons from other parts of the sample. This is especially useful for studying materials that are not uniform, such as mixtures or polycrystalline samples. The resulting pattern shows the arrangement and distances between planes of atoms, helping scientists determine things like the crystal's orientation, type, and perfection, and even spot defects or identify unknown materials. SAED is essential in material science because it allows researchers to analyze the structure of incredibly small regions with high precision, something that bulk techniques like X-ray diffraction cannot do as effectively. To interpret selected area electron diffraction, SAED, as an undergraduate, think of it like shining a very thin, powerful beam of electrons through a tiny spot on your sample using a TEM, and capturing the pattern these electrons make after bouncing off the atomic layers. The result looks like a set of bright spots or rings on a screen. Each spot or ring represents a special way that atoms are stacked in the material. If you see spots, you have a single crystal, very orderly atoms. If you see rings, you have many tiny crystals with atoms lined up in lots of directions. By measuring how far these spots or rings are from the center, and using a standard formula that involves the electron wavelength and the camera setting of your microscope, you can work out the distances between atomic layers, just like finding the spacing between bars in a fence by looking at their shadows. Comparing these distances to textbook data lets you identify the type and orientation of the crystal. This process helps scientists quickly check the structure, quality, and sometimes even the kind of material they have, all from just one tiny area of the sample.